heterogeneous equilibria. I bet you didn't realize, but so far we've only had gases in our chemical equations. So we call that a homogeneous equilibrium. But that doesn't always happen. Sometimes we can have equilibrium be reached when we have more than one phase or more than one state of matter. And so these are called heterogeneous equilibria because there's more than one state of matter. So for example, the decomposition of calcium carbonate, CaCO3, which is a solid, into calcium oxide and carbon dioxide gas, this is a heterogeneous chemical equation. Okay, so from experiment, we found that if you have a heterogeneous equilibrium reached, that it does not depend on the amounts of pure solids or liquids present. The reasons for this is that the concentrations of pure solids and liquids can't change. And since they can't change, they shouldn't have an effect on the equilibrium or on the equilibrium constant. So because solids and liquids don't have an effect, their concentrations are not included in the equilibrium expression, the K expression for the reaction. So example 5 is writing a K expression when you don't have to include everything. Okay, so we want to write the expression for solid phosphorus pentachloride that decomposes to liquid phosphorus trichloride and chlorine gas. And we want to write them for deep blue solid copper 2 sulfate pentahydrate that's heated off to drive off water vapor to form white solid copper 2 sulfate. So our first reaction has phosphorus pentachloride, so PCl5, decomposing into phosphorus trichloride and chlorine gas. So the states of matter are important this time. We can't just leave them off because they're important for us to know what to include. Okay, so the PCl3 is a liquid and the PCl5 is a solid. Well, when writing our K expression, the solid doesn't matter, so we are not going to include that, and neither does the liquid because their concentrations don't change. Okay, so the K expression will just be with the Cl2 gas. And since it's on the product side, we can put it in the numerator where we have the concentration of Cl2, and sorry, I didn't tell you already, but it's balanced, so we don't have an exponent, and that is our K expression. For the Kp expression, we're just going to do the same thing, except this time, instead of writing brackets to show concentration, we're going to show the partial pressure of the chlorine gas. And that's it. So then for our other example, or other part to the example, the other equation, we have copper 2 sulfate, so that's CuSO4, pentahydrate. We've seen these before in our reviewing for the AP exam with our e-learning days. But if it's a hydrate, you add waters. And since it's penta, there are 5 waters added on to this solid structure. Okay? That's decomposing down into the copper 2 sulfate. That's white, so that means that's the copper 2 sulfate without any hydrate on it. And that's also a solid. And then we have that water vapor that's been driven off. So we have H2O gas that's been driven off. But since we had 5 pentahydrates, 5 waters added onto that structure, that means that we need to balance it with a 5 in front of the H2O. So this time, the only thing different about our K expression, of course, besides just filling in the correct composition inside, is that now we have a 5, so it's to the 5th power. Same thing goes with the Kp. The partial pressure of the water will be to the 5th power. If it was in the denominator, we don't have an example like this, but what if instead it was the opposite, where we took PCl3 plus Cl2 to form the PCl5? Well, in this case, the Cl2 is on the reactant side, so if we would write the K expression of that, we'd have to put 1 over the concentration of the Cl2. So if it's on the reactant side and everything else crosses off, you have to have 1 over that. It's the inverse because of the rules from writing your K expression. So we can apply the equilibrium constant in many different ways. So it allows us to predict several things. The tendency of the reaction to occur, whether a given set of concentrations are actually at equilibrium, and the equilibrium position that will be achieved from initial concentrations. So just an FYI, a more descriptive and colorful account of this is on pages 618 to 620 in your book, if you're interested or you don't really get it from the video the first time around. So, the extent of a reaction. The inherent tendency for a reaction to occur is indicated by the magnitude of the equilibrium constant. How big is the equilibrium constant? Okay, so if the constant is greater than 1, this means that at equilibrium, the reaction system will consist of mostly products. So the equilibrium lies to the right. If you, sometimes, instead of saying right or left, sometimes we draw arrows. So if you want to draw an arrow, there you can. So when it's greater than 1, it's favoring the products, and so that it's already on the right side. If it's less than 1 at equilibrium, that means that the system contains mostly reactants, so the position is far to the left. So it's heavier on the left side than the right side. More reactants than there are products. The size of K and the time required to reach equilibrium are not directly related. The time required to achieve equilibrium depends on the reaction rate given for the reaction, chapter 12 stuff, and the size of the activation energy, also chapter 12 stuff. So K is determined by the thermodynamic factors, such as the difference in energy between the reactants and products. So it's more dependent on the reaction rate. The size of it isn't, but what it will be is reaction rate and the temperature or energy involved. Reaction quotient is what we use when we don't know for sure if it's at equilibrium. Okay, so sometimes we'll mix chemical reactions together and they don't reach equilibrium. And so if it's not at equilibrium, we will want to shift it to be at equilibrium. And so we use the reaction quotient to figure that out. So if the concentration of one of the reactants or products is 0, the system shifts in the direction that produces the missing component. That's nice to know because it's shifting towards whatever is 0. But if all of the initial concentrations are non-zero, it becomes more difficult to determine the shift. So we use the reaction quotient Q instead. To find the reaction quotient, the law of mass action is applied, so see level 58, where you take products over reactants, use the coefficient as the exponent on the concentration. So for example, the synthesis of ammonia reaction, and in case you forgot, we've used this a lot, is nitrogen gas plus 3H2 to form 2 NH3s. That's where they got this quotient reaction from, where you take products over reactants, still the same way. Okay, the equation is back in example 2. The little zeros, that means initial concentration. So you'll usually be given those in the problems. Okay, so if we can figure out Q, because that's pretty easy, just like solving for K, then we'd have to know how to compare it to the K's that we should have at equilibrium. Well, when Q equals K, the system is at equilibrium, so nothing will happen. There will be no shift. But if Q is greater than K, the ratio of the concentrations is too large. To reach equilibrium, products must turn back into reactants. So this system will shift to the left, consuming products and forming reactants until equilibrium is achieved. And so the reason why we say shift to the left is because, like for example, with the synthesis of the ammonia, normally we would think, oh, okay, the nitrogen and the hydrogen will form into the ammonia. But this is saying that we have too much ammonia, we have too much product, okay? And so the product must turn back into the reactant, so it will shift left. The arrow direction will be left towards the reactants so that more reactants will be formed, okay? The opposite is true if K is less than, or sorry, if Q is less than K. So if Q is less than K, that means that there's too much reactance. There's not enough products. So the system will shift to the right, meaning that we will have our normal thought of equation where the reactants will form to make our product until it reaches equilibrium. And so then when it reaches equilibrium, the shift will stop. This picture is in your book. It's on page 621. And as I included it in your notes just in case this is easier for you to understand than all the words. Maybe a pictorial reference would be good for you. Okay? So for example 6, we're going to see what happens here if it's how Q compares to the K. So for the synthesis of ammonia, which we've just been using those equations, at 500 degrees Celsius, the equilibrium constant is 6.0 times 10 to the negative second. So that's K, all right? Predict the direction in which the equilibrium will shift to reach the equilibrium in each of the following cases. So we're given concentrations, initial concentrations for both cases. So what we're going to do is we're going to solve for Q and then compare Q to K and figure out the shift. So our equation, again, is the N2 plus 3H2. I'm not putting gases because they're all just gases, so we include them all. And to make 2NH3. So let's next write our Q expression, our reaction quotient. So we have products of reactants, so we have the NH3, and since there's a 2 in front, we need that squared. And putting the 0 to show that we are going to plug in the initial concentrations there. Then we have N2, doesn't have a coefficient, and H2 has a coefficient of 3. Alright, so for set 1, the top one I'm going is set 1. Okay, for set 1, let's plug those into and find out Q. So the concentration of the NH3 goes on top. And that is squared over, then the N2 is 1.0 times 10 to the negative fifth times 2.0 times 10 to the negative third cubed. Be careful typing in your calculator. Order of operations is super important. When you solve it out, Q is 3.7 times 10 to the 7th. Or sorry, 1.3 times 10 to the 7th. Alright, so now we need to compare to K, which we said up in the problem that K, the equilibrium constant, is 6.0 times 10 to the negative second. Okay, well comparing these two numbers, times 10 to the 7th compared to times 10 to the negative second, times 10 to the 7th is humongous compared to that. So Q is greater than the K. And since Q is greater than K, that means that we have too much product, so our reaction will need to shift to the left. Or if you would rather write it like this, you can also shift by writing like this, where you point your arrow towards the reactants. Okay? So that you take those products that you have too much of and turn them back into reactants. Okay, so that was set 1. Now let's do set 2. Set 2, Q this time equals 2.00 times 10 to the negative 4. Gotta square it over 1.5 times 10 to the negative fifth. Be careful again when you're solving and typing in. Q I got to be 0.060. If we put that in scientific notation to help us compare, that is moving twice to the left. 6.0 times 10 to the negative second. Well, hey, guess what? Q equals K. So that means that there is no shift happening here. because they are already equal.